Hello everyone. So in this video I'm going to look at 3 more problems from chapter 36, all of them related to Lorentz transformations. So the first one is problem 30. In the Old West we have a marshal riding on a train traveling 35 meters per second who sees a deal between 2 men standing on earth 55 meters apart parallel to the train. The marshal's instruments indicated in his reference frame 2 men fired simultaneously, and which of the 2 men, the first one that the train passes, which will denote A, or the second one, which will denote B, should be arrested for firing the first shot, that is, in the gunfighter's frame of reference, who fired first, and how much earlier did he fire, and who was struck first. Okay, so okay, so this is problem 30. So we have 2 gunfighters, and yeah, there's some separation between them, and we have a marshal that's on a train. Right, so and the train track is just parallel to the line that's separating these 2. Well, this train is moving at 35 meters per second. In the marshal's reference frame, they're separated by 55 meters. And again, in the marshal's reference frame, we are going to have these 2 firing their shots simultaneously, right? So this is the picture we have. I also need to make this a little bit formal. So what I'm going to do here is that I'm going to choose 2 reference frames. So in our usual configuration, so this is X, Y, and Z. Let's call this reference frame S, and another one that's moving with some velocity in positive x direction with respect to the first one, X prime, Y prime, and Z prime, with some velocity V. And I'm going to choose this to be the marshal's reference frame, and this is going to be the ground reference frame. Okay? So this V is just 35 meters per second. So from what they give us so there are these 2 events that I'm going to call again A and B, even though they're calling just the gunslingers A and B. I'm going to call the firing of the shots by these gunslingers A and B. So this person firing first is going to be event A, or this person firing is event A, this person firing is event B. Okay, so we are told, first of all, that these things take part 55 meters apart. So without loss of generality, I can actually choose one of them to be at the origin, and then the other one is going to be at 55 meters. And we are told that this actually take place at the same time. Actually, I chose this as the frame, prime reference frame, so it looks like this. So XA prime is at 0, XB prime is at 55 meters, TA prime is equal to TB prime. Okay? And we are going to be comparing TA and TB, right? So which one is earlier, which one is shorter? So we can just take a look at which one, just take a look at their difference and see whether it's smaller or larger than 0. Okay? So to do that, what we need to do is to write down the expressions for these, which are actually in the book, and just make a simple subtraction. Right, so TA, actually, I think I have them here. Yeah, so TA is just gamma times TA prime plus V XA prime divided by C squared, and similarly TB is just gamma TB prime plus V XB prime over C squared. So I just took these from the book, and I can take their difference, so subtract them side by side. These are equal to each other, so they're just going to cancel, and I'm going to end up with this expression that so it's gamma V XB prime minus XA prime divided by C squared. Right? And so because this is larger than 0, all of this are larger than 0, this is going to be larger than 0. So TB is larger than TA, which means that A shot first. Okay, so in the ground reference frame, this person shot first, and because the marshal is moving with respect to them, they actually see this as taking place simultaneously. Right? And then in part B, they are asking how much earlier did he fire. So this we already calculated this. So you just need to substitute this 55 meters here, the velocity 35 meters per second over there. You'll need to calculate the gamma factor with that v value, and then just carry out the algebra. I'm sure it's going to be something very, very small. And then for part C, they're asking who was struck first. And then in the solution manual, so there's a solution that's given in the solution manual, which I want to show you, which actually I accidentally already showed you. So they say that in the Earth frame of reference, since A fired first, B was struck first. Yes, this is fine, I agree. In the train frame, A is moving away from the bullet fired toward him, and B is moving toward the bullet fired toward him. Thus, B will be struck first in this frame as well. I don't think this actually explains everything. So they're saying for one of the gunslingers, the bullet is going to travel a shorter distance, which I agree. But from this, it doesn't follow that B is going to be struck first, because the bullet's velocities are going to be different. So presumably, they fire same kind of guns, and in their reference frame, the ground reference frame, the speeds are going to be the same. In the reference frame of the Marshall, they're not going to be the same. And because of this, just because one is going to be traveling a shorter distance, one of the bullets is traveling a shorter distance, doesn't mean that it's going to take place earlier, because the speeds are going to be different. Now, I'm not going to solve this problem completely because it's quite complicated, and in fact, there is a simple way to solve this by using the so-called Minkowski diagrams. And we don't cover Minkowski diagrams in this course, but if you take a course on special relativity, you will see. We'll learn about Minkowski diagrams, which are also called space-time diagrams. All I'm going to say is that it depends if the velocity of the bullets, the answer is not obvious, it depends on whether the velocity of the bullets is larger or smaller than 35 meters per second. And I think it's very reasonable to assume that it's actually larger than 35 meters per second. And then you get a certain answer that way, but as I said, I'm not going to actually solve it. So if the bullet is actually moving slower than 35 meters per second, well, the answer is correct in the case that it's larger. The speed of the bullet in the ground frame is larger than 35 meters per second, but if it's slower, then you actually revert the answer. Okay? Right, so that's all I want to say about this. I'm not going to go into the details of the solution. It's quite complicated. And you're certainly not responsible for it. So for problem 32, we have an observer in the reference frame S who notes that two events are separated in space by 220 meters and in time by 0.80 microseconds. How fast must reference frame S prime be moving relative to S in order for an observer in S prime to detect two events as occurring at the same location in space? Okay, so let's take a look at this one. Let's first erase this. So by the way, one way to answer the question is to really just substitute some numbers for the velocity of the bullet and proceed that way. So you will see that you get actually different answers for different bullet velocities. So this is problem 32. We have an observer that notes two events are separated by space in 220 meters. So xb minus xa, let's call these events A and B, is 220 meters, and they're also separated in time by 0.80 microseconds. So TB minus TA is 0.8 microseconds. Now, of course, I don't know for sure if B comes first and A comes first. It's possible that this is positive and this is negative and so on and so forth. So just to be safe, you could just put plus or minus here, something like that, or plus or minus in at least one of them. But I'm just trying to write down what is given in the problem without going into detail. So this is just a reminder for me that I don't actually know that both of these are positive. One or both can actually be negative. So we want to detect these two events as occurring at the same location in space. So we want our xb prime to be equal to our xa primes. All right, this is my notation, which is, I think, unusual, that's requiring for an equality to hold. So how do we proceed in this case? Just like the previous problem, I'm just going to write, xa prime. I'm just going to write expressions for xb prime and xa prime, and I'm going to just set them equal to each other and see what drops out. So xb prime is going to be gamma, again this is from the book, xb minus vtb, and xa prime is equal to gamma xa minus vta. Okay? So I want these to be equal to each other. I want these to be equal to each other. So if I do that, I can calculate an expression for v, and what I'm going to do, so if I equate these two equal to each other, then the gammas cancel. So xb minus vtb is going to be xa minus vta. I move this to the other side, move this to the other side, and then I can move times to the denominator. And okay. So I think v comes out to xb minus xa. So this goes over here, this becomes minus, this goes over there, this becomes over a minus tb. So it turns out that one of them was in fact negative. So I will get or it's moving in the negative x direction. So that's also possible. If it's moving in negative x direction, then we will see both of these to be positive. But the speed that we're going to observe is just going to be the absolute value, the ratio of the absolute values of these. And we can just carry out that calculation. I think it's not very hard. Okay, are they asking anything else? No. So for such an observer that's moving in this speed in this certain direction, the two events are going to be simultaneous, right? Sorry, they are going to take place at the same location, not simultaneous. I'm sorry, I misspoke. Okay, so next question is 76. We have a rocket A that passes Earth at a speed of 0.65 c. At the same time, rocket B passes Earth moving 0.85 c relative to Earth in the same direction. How fast is B moving relative to A when it passes A? Okay, so again, let's take a look at this. So from the way I read this, it will actually pass the other rocket at the very beginning when they're both passing by Earth, right? But maybe I misunderstood. So let's say this is Earth. This is problem 76. Yeah. Okay. And I have a rocket A that's moving at moving at 65% of the speed of light. V is 0.65 c, moving in a certain direction. At the same time, rocket B passes Earth moving 0.685 c relative to Earth in the same direction. So I have rocket B moving in the same direction and passes Earth at the same time. So yeah, indeed this will pass the other rocket at the same time as it passes Earth at 85% speed of light. How fast is B moving relative to A when it passes A? Okay, so this is an application of the velocity addition formula from Lorentz transformations. So let's write the formula and try to formulate what goes there. So that formula is u of x is equal to ux prime plus v divided by 1 plus ux prime times v divided by c squared. Okay? So I normally write this as u subscript x prime, but the book is putting the prime on the u rather than the x subscript. So I will try to follow the book's convention, so you'll get less confused. So we are going to apply this formula, and there is a way to apply this formula taking a shortcut, but I'm going to try to do this more formally. So in the end, what we are trying to do is to calculate the velocity of B with respect to A. Is that what they're asking? How fast is B moving relative to A when it passes A? So this ux prime, ux is going to be the velocity of B with respect to A. Okay? So if we draw our coordinates, so what does this look like? This is an x, y, z, let's say for the reference frame S, and we have x prime, y prime, z prime and this reference frame is moving with some velocity v in the positive extraction, and we have some velocity u, right? So either we are measuring this with respect to s or s prime. So we are saying that this u is going to be our velocity with respect to a. So I'm going to call this the rocket ship B. So this is rocket B, and this is going to be the s prime is rocket A, and naturally this has to be Earth, right? Okay, then this v is velocity of Earth with respect to a, right? That's the velocity. This v is the velocity of the reference frame s prime with respect to s, but that's just velocity of Earth with respect to rocket A. And finally, u x prime is the velocity of b with respect to Earth. Is that right? I think so. Okay, so this is what we're looking for. The velocity of Earth with respect to A and the velocity of B with respect to Earth. This is easy. Right, in this reference frame, the velocity of with this choice of coordinates for the reference frames, the velocity of Earth of B with respect to Earth is just 0.85 c. You have to be careful about this one, the velocity of Earth with respect to A. Again, this choice of coordinate system, these signs and everything, this has positive velocities in the positive extraction. Earth with respect to A is going to be moving in the negative extraction. So this is going to be negative 65c. Right? So once you put this out formally, it's just a matter of substitution here. Your answer is going to be 0.85 minus 0.65 c divided by 1 minus 0.85 times 0.65. Right? So you could either say that this is the formal result that comes out, or if you want to take a shortcut, which I'm not encouraging you, but you certainly can do it, you can say that this is my velocity addition formula, and for velocity subtraction, when things are actually moving in the opposite direction, you just pick up a negative sign. Right? So here I'm subtracting off 0.65 velocities from 0.65 c from 0.85 c relativistically. Right? With the Gaussian transformations, you'll just get what is in the numerator. With the Lorentz transformation, you get an additional factor in the denominator. Right? Same thing with velocity addition. If you're adding 0.65c to 0.85c, what you will get in the Gaussian transformation is just what we will find, a simple addition in the numerator, whereas with the Lorentz transformation, you have an additional factor that's in the numerator. Okay? All right, so that's all I want to say, I think.